Bismillahirrahmanirrahim. Today's topic is boundary conditions by the penalty method. Now, this is slightly different from the method that we have encountered earlier, namely the elimination method or the partition approach. And the difference is that in the methods that you have studied to date, if there is a boundary condition to be applied, for example, u1 is equal to 2 millimeter. This is just one boundary condition that you need to apply. You apply exactly 2 millimeter on that boundary condition or at that node. Now, in penalty method, we apply this, for example, u1 is equal to 2. We don't apply this directly to the degree of freedom in question, but we apply it through a spring with a very high stiffness C. Now, if you apply 2 millimeter here, then this is your degree of freedom that you need to apply this boundary condition on. So instead of applying this 2 millimeter here, this is, let's call it degree of freedom 1, you apply it here through a spring. So what is applied here is not exactly 2 millimeter, but something very close to 2 millimeter. So in this way, this method is not exact. Now, by exact, I mean it will be very close. For example, you may be able to apply 2 millimeter here, and here you will be able to apply something like 1.9999, something like this, or 2.00001, something like that. So as far as your FEM is concerned, there's nothing to worry about here. But if you compare this with the partition method, then you'll be able to apply exactly 2 millimeter. But that's not a big problem for us, because on the plus side, this is much simpler than the partition approach. You get to save a lot of computational effort here. So let's see how we go about applying boundary conditions by the penalty method. Now, we'll be applying both the zero boundary condition as well as the non-zero boundary condition. So this method is capable of applying both. So we'll demonstrate an example. So here we'll be departing from the matrix that we've been using for partition method, because we don't need to partition anything here. So we're going to basically solve a different question here, and I'll choose a question that shows you the zero as well as the non-zero boundary condition. But before that, we have to start from the beginning. We have to start from probably the first concept that you learned in this course, minimization of potential energy. Very familiar to you by now, because even after that we have done it at least 2-3 times since then. And this is very useful for stress analysis problems, and because we are focusing on stress analysis problems, let's start from this. And this is the expression for total potential energy. This is the expression for strain energy, and this is the work potential. Now we know that for equilibrium, this potential energy is minimized, of the whole system is minimized. So first of all, let's write this in detail here. This is again a very familiar expression for you, nothing to be intimidated by here. Similarly, this is your expressions for strain energy and the work potential. Now it's just a simple repetition of what we have been doing already, and you know what this matrix is. This is the displacement matrix of the system. This is the displacement matrix. This transpose is only because you have to multiply these terms together. This is the stiffness K matrix. the system stiffness matrix. Now, if you consider equilibrium, for equilibrium, we differentiate this total potential energy with respect to all the degrees of freedom in the system, namely the u vector, the system u vector, and you put it equal to 0. And this gives you, this is, we have seen this, this is, you can consider this as the square of this u matrix, u vector, and it works quite like an algebraic expression, and we have seen that. So you are left with ku is equal to f. This is the fundamental FEM equation for equilibrium steady state problems. Now if this is n into n, then this is n into 1, and this is also n into 1. You are familiar with this whole thing. Okay. Now if we write it in an expanded form, this is nothing but, again this is very familiar to you, k11, k12, k13 up to k1n. Then you have k21, k22, k23, and then k2n, whatever the number of this system, how big that system is, depends on this number n. Similarly, k31, k32, k33, and so on, and then you have k3n. And finally, again, there is some terms that are missing here, and because we are talking about general system, then you have kn1 and kn1, kn2, kn3, knn. This is your total system. And the U matrix, U1, U2, U3, and so on up to Un. Similarly, the force vector F1, F2, F3, Fn. So this is as far as this expanded form of this is concerned. It's very familiar to you. Nothing new about this. Now, let's call this A, because we are going to use it next. Very soon we are going to utilize this expression. Let's remember this as equation A. Let's move on. And come to our penalty method. This is just the preliminary. This was the preliminary part. Now we are going to focus on our penalty method. Now let's say there's a system here. You have this body of interest, and you have some sort of meshing here or whatever that is, but this point is of interest. Now this point, maybe call it node n, whatever node it is, and this is the degree of freedom on which you want to apply a certain boundary condition. Okay, so that boundary condition, let's call it u1 is equal to a1. Let's call this degree of freedom u1. This is the u1 degree of freedom, and you want to apply a1. a1 is a constant, a number, for example 2 millimeter, 5 millimeter, whatever that is, it's a number. So where we depart from the traditional methods is, instead of applying u1 is equal to a1 on this node, like I mentioned earlier, I'm going to use a spring with a stiffness C, high stiffness. We'll talk about how high this stiffness needs to be. And what we do is we move this side of the spring by a distance a1, not this point. Now, because this spring is a very stiff, it's a very stiff spring. If it was of infinite stiffness, it would have been a rigid bar. So in that case, a1 would have been equal to u1 is applied here. That would have been equal to here. You would have been able to apply a1 here also. But this is although it is of a very high stiffness, it is still not a rigid bar. So there will be some sort of compression here, and the load applied here, the displacement that you'll be able to apply here will be slightly different from A1. Okay, so you apply the A1 instead of here, you apply it here, so you end up applying a displacement boundary condition which is actually very nearly equal to A1 but not A1. So this is why this method is not exact in that sense. It will be very close to the real solution, but it's still somewhat approximate. Now I'm not talking about the numerical error here. This is something else. Numerical error is the error like you have a value like 6.6666 and then you store it somewhere, you round it to maybe 6.67, you lose some significant figures there. So that's what I'm not talking about, that sort of error. I'm talking about this real difference between what you apply here and what actually gets applied on the boundary condition, and we'll look at it presently. Now this net extension in the spring, net extension in the spring will be nothing but u1 and recall that u1 is not equal to a1. Otherwise, if u1 is equal to a1, then this is a rigid spring and then there is no net extension. So net extension is u1 minus a1, and the way I've drawn this, it will be negative. Actually it will be compression, but this expression will give you the tension or the compression, whatever the case is. Now the strain energy in the spring. What about the strain energy in the spring? Because now recall that when we were talking about the minimization of energy in the traditional system, there was just these two terms, because you were applying the boundary condition directly here. You didn't use a spring or anything like that. So this covers that. But now that you are going to use, this is your system, but you have added a spring here. Now the strain energy in the spring also must get added to your system equations, and that is nothing but, strain energy is simply nothing but 1 over 2 C u1 minus a1 square. Let me explain this term. The strain energy is, this is the load, this is the deflection of a spring. For example, you have this sort of reflection, then the strain energy is this area under the curve. So strain energy is basically half into this. Now if you utilize the fact that this K is nothing but F over deflection, then you can replace F by K delta and you get 1 over 2. So this is nothing but 1 over 2 K, 1 over 2 K this, and that is what we have used here. 1 by 2 is this, K is stiffness, spring stiffness, we call it C here, the same thing, you can call the rows by any name, and this is the deflection in the spring. If obviously if u1 and a1 are the same, if this is a rigid spring, then this deflection will be 0, so there is nothing to be added here. But that is what we are not doing here. We are applying it through a spring which is very stiff, but still some sort of error is there, some slight difference of the boundary condition that gets applied here and that you intended to apply, and that is the basis of this, the difference between this method and the last methods. So now if you want to minimize the energy of this system, then obviously there will be an additional term. Now the total potential energy will be, this part is the same because you'll have strain energy in the different parts of this body, is just partially drawn here, but you have this some body here, so it has all the degrees of freedom and whatnot. But now in the strain energy term you have this term also, which didn't used to exist here. And finally this is again the old term. These two terms are familiar to you. This is the new term which is only visible or which is only relevant when you're talking about the penalty method. And if you again differentiate it with respect to all the degrees of freedom in the system, put it equal to 0. This is called the minimization. This is minimization. Very familiar to you. So you get something like A. Why A? Because for this term and this term, if this term, you forget about this term for a moment, this term and this term minimizes to this A. We only need to additionally consider this term here. So A plus differentiation of this with respect to all the u's, but in this case only u1 matters because you're only applying degree of freedom, boundary condition to degree of freedom 1, which is u1. So, and similarly, if you have many u's, then you can differentiate with respect to all those u's. You'll have different expressions here also, but in this case the only relevant thing is differentiate with respect to u1. 2 comes down, gets cancelled, c u1 minus a1, and then u1 is 1. So basically this is your expression, or in other words, a plus cu1 minus ca1 is equal to 0. This is your expression including the spring and the original system that was there. So now what is left for us is very simple. What we need to do now is, in this A, we need to add this expression. Now, if you consider this expression, it's very easy to do. The C gets multiplied by U1. This term gets multiplied by U1. Okay. So you just, because we're talking about this boundary condition on this, so if I only add plus C here, then I'll be able to incorporate this term. As far as this term is concerned, this doesn't multiply with any U. This is a constant. So constant terms, because all these values are being multiplied by some u. So now what we do is, this thing has to be taken to the right hand side where we have constant. So this you take to the right hand side and you simply add in this row f1 plus ca1. That is simply all you need to do. This you write c here. This is the only change that we do as a result of this addition of this spring, plus ca1. I change the sign of ca1 from minus to plus because it goes to the other side. Now the c multiplied by u1, this again makes this expression fully reflected here. So now this is your change in your matrix. Now that is all you need to do. So let me summarize this. Simply, the two things that you have to do is, for any boundary condition u1 is equal to a1, and it could be u2 is equal to a2 or u3. It can be others also, but let's talk about this. Simply add spring stiffness C to K11. So now I think it's very easy to understand. If it was U2 is equal to A2, for example, then you would simply have multiply this. You have added C here, K22 plus something here. So this can be extended to all the degrees of freedom. This is simply number 1, add stiffness, spring stiffness C to K11. Number 2, add CA1 to the force term F1. Similarly, if it was, for example, F2 or Fn, whatever, then you would have taken, you have CAN to this. But in that case, C would have been added to this one. That is all you need to do as far as this system is concerned, and your boundary conditions will have been applied. Now this is as simple as that. Doesn't get simpler than that, right? Now one thing remains. Let's not be hasty and think that the work is done. Almost done, but not quite. So let's discuss the problem of choice for C. If I expand the relevant equation in this system, the relevant equation is this first one, because we are applying a1 to u1. So this is the first one is the relevant equation. K11 plus cu1 plus k12 u2 plus k13 u3 and so on. K1 un is equal to f1 plus ca1. So if I expand it like this, I simply get k11 plus cu1, k12 u2 plus k13 u3 and so on, and then you have k1 and un is equal to f1 plus ca1. This is nothing but the expansion of the first equation. The first equation is relevant because we are applying the boundary condition of the first equation. Now, if we divide all terms by c, all the terms by c, then we get k11 over c plus 1 u1 plus k12 over c u2 plus k13 over c u3. Then you have k1n over c un is equal to f1 over c plus a1. Now, if we arrange that c is much greater than k11, k12, k13 up until k1n, if you make sure that in all the case, the values we generally know about the case, we know when we are solving this, we already know what the values of all these k's are. So if we arrange for c to be much greater than that, and by much greater, I'll explain what I mean here, then you can see that this becomes very small number, so you can call it 0. This is again 0, this is again 0, not exactly 0, but it tends to 0, very close to 0. And if k's are much smaller than c, then f1, if you have any experience with FEM, f's are generally much less than the k's also. So again you have 0. So provided this situation prevails, then in your case u1 is nearly equal to a1. Now this one was for one boundary condition u1. You may have u2, u3 boundary conditions, or somewhere down the line you may have other boundary conditions also. So a safe method is, instead of only looking at this one line, you just look at all the K matrix, the whole K matrix, and find out the maximum Kij value. And generally you will find that value most probably in one of the diagonal elements. But basically we're talking about the maximum value at K1, Kij, and simply multiply it by 10 raised to the power 6. This is what your C should look like. And I 1 to n, j 1 to n. So we're talking about the whole matrix. Now, where does this 10 raised to the power 6 come from? In some books it's 10 raised to the power 4, in some it's 10 raised to the power 5. I'm using the value in your textbook. It is quite satisfactory. Even for 10 raised to the power 4 is alright. So interested parties should use this value. I'm going to use in this value to illustrate an example problem, but even if you use 10 raised to the power 4, you'll see that it's not much different. But if you use 10 raised to the power 6, there's nothing to worry about. It's much beyond the levels of accuracy we normally require. So that should be the end of that. One final point, and that is, what about the reaction force? Now if I again come back to this, if I apply A1 here, and as a result of this A1, because if this moves here, then this also moves here, and this is your U1, which will be slightly different from A1. So if I apply it here, then the original was this point, but now when it moves here, then your point from this to this point, it moves to this, and this is your body. Now the deflection here, the extension will be U1 minus A1. Now if this is the case, then it's very easy to see that this is actually compression. So if this compression is there, if it is being compressed, then the force that is applied at this point, it has to be reaction force is equal to C multiplied by U1 minus A1. But this force, if we look at it at this point, this R1, this is actually extension. But in this case, because U1 is less than A1, it will become negative. If it was positive, it could be the other way around. If it was positive, let's say this is positive. If this is positive, then you can see that the spring actually should have been pulled like this if it is positive. So we talk about this one, the reaction force at this point, it is in the negative x direction. This is the x direction, negative x direction. So you need a minus sign here. If on the other hand it is negative, as is the case here, and this case is something like this, being compressed, so the force must be in this direction. So now again, if you talk about U1 minus A1 is negative, negative multiplied by again negative, it gives you positive. So this negative sign still has to be there in either case. So whenever we want to find out the reaction force, irrespective of whether ultimately it's a tension or a compression or whatever it is, your expression for reaction force will always be minus C U1 minus A1. Now this minus C, this minus sign will adjust the compression or end compression in either case. And the final point is that this U1 will not be equal to A1, because there is a slight difference between U1 and A1, and that difference is very important here. If U1 and A1 are the same, then you have no reaction force. It doesn't make any sense. The reaction force has to be there. If it has zero boundary condition or some boundary condition fixed, there must be a reaction force, and that reaction force is achieved by the small distance between the two, small difference, and then you multiply this with a large number and you get the reaction force. I'll illustrate this principle, the use of these equations, in an example. So let's take this problem and apply the penalty method on this. The good thing about this problem is that you have a zero boundary condition here and you have a non-zero boundary condition here. So this time I'm using a real example, and I'm not making use of that dummy matrix, that 6x6 matrix that I used to demonstrate the partition method. Here meshing is very simple for this. This is your node 1, 2, 3. This is element 1, this is element 2, and the rest of the procedure is very simple. I'll focus on the penalty method, but let's construct the stiffness matrices. You have AE over L. A into E is 200, 10 raised to power 3. I'm using the Newton, megapascal and millimeter system. AE over L, L is 150, and you have this 1 minus 1 minus 1, 1, very familiar to you by this stage. And this turns out to be 333.34. You have 333.34. Actually this is 0.3333, something like that, but we have to cut it somewhere. So there's some loss of accuracy here, but you have seen that it doesn't matter. Now this is K1, and if you see this problem, K2 should always have the same, it should also have the same value, because the length, the area and the material, it's the same. You're talking about steel here. So K2 is also same. Now when we talk about connectivity, element 1 is connected to the nodes 1 and 2. Element 2 has nodes 2 and 3. So it's again a very familiar process for you. K this comes in this space and this one comes in this space. 2 is common, so you will have something like this. Again, a very familiar process. This is not the topic for today. I'm just going through it quickly. This now here you add this and this add together, because there's a 3333 here also. These two add up, and so you get 666.68. Here you again get 333.34. 0 here. You know why you have zeros here. No element connects these 1 and 3 nodes, so you'll have a 0 here. And then again 666.68. I'm sorry, this is 3. It should be 3, 4. This thing comes straight here. This is not 666.34. This is same thing here. And you have all those properties that you have this. Add all the rows together, there will be 0 and all that sort of thing. This is symmetric. All positive values on the main diagonal, principal diagonal. Now you have this K matrix, and then the displacements U1, U2, U3, and the F matrix. Force, applied force 0 here, 6 0 0 0 0 here, and 0 here. Now we encounter a problem, again a familiar one to you. We are not sure whether, as a result of this force, whether this end touches this wall or not. If it doesn't touch the wall, then the wall, for our purposes, the wall doesn't even exist. If it does, then you have to apply that boundary condition too. So we don't know in advance. So what we do is, at this point we all only know that u1 is equal to 0. Using the elimination approach, again I'm not demonstrating the penalty method here. Elimination approach will mean that you will just eliminate this row and this column. You'll be left with this 2 into 2 matrix, invert it and find the value of u2 and u3, and you should get something like, please verify this, 0.18 millimeters. This should be the value that I would like all of the students to verify this calculation for themselves. So now, as a result of this calculation, we know that wall does play a part. So this will touch the wall, this end. So now we have to do this problem again. By again I mean we have to apply the boundary condition again. And I'll just write down the matrix one more time. It's somewhat tedious, but please bear with me. And now here you'll see the power of the penalty method. To this point I have not used penalty method, I just used the elimination approach. Here I'll use the penalty method both for the 0 as well as there's a non-zero boundary condition also now. I'll close it later on. I'll close this parenthesis later on. Now we know that u1 is equal to 0. Very obvious here. u1 is 0 and u2 is 0.12 now, because if the wall wasn't here, this would have exceeded this, but the wall will stop it at 0.12. So we know u1 is equal to 0, u3 is equal to 0.12. We know this. Boundary conditions now. u1 is equal to 0, u3 is equal to 0.12 millimeter. Now, what do we recall from the development we had before penalty method? Wherever you have to apply the boundary condition, whether it's 0 or non-zero, you select the biggest k number, which is obviously this one, and you add it to the diagonal element for that boundary condition. For example, here you take, this is u1 and u3, here and here you have to add 666.68 into 10 raised to power 6. It's a big number now. Similarly, 666.68 into 10 raised to power 6. This is what you add on the diagonals, u1 and then u3, this k11, this k33. Now what about the right hand side? You also add this number c, this is number c, multiplied by a1 here, and you add number c multiplied by u3, u1 or u1 here, u3 here. Now this is 0, so even if you add ca1 here, this actually is a, recall that although these are the boundary conditions, but what we do is we apply a1 values here, which are these values, but in the end you won't have exactly these values applied here. You will have slightly different values, so doesn't matter. This is ca1, this is a1, this is a3 now, constant values. So this becomes again 0, so you don't add anything here. But when it comes to this, you now apply 666.68 into 10 raised to power 6 into 0.12. This is nothing but ca3. Now that is all you need to do. Now compare how simple this system is as compared to the partition approach. You have to do so many things in the partition approach. Even in the method 2, which is a simpler one, even that takes a lot of effort. This is all you have to do. So now you have this new matrix. I leave the students to verify the, you have these values, these will change, and you will have then u1, u2, u3, and on the right hand side you will have these values. Please verify your calculations. And now this matrix, this one, boundary conditions have been applied. This is a non-singular matrix which you can invert. So for now, because solution is our next topic, we haven't discussed any algorithm for solution to date. So this is a 3 by 3 matrix. You can use your you may use your calculator, or you can use some Excel function. For example, for inverse you can use the m inverse function in Excel. For multiplication, once you have inverted this, you have to multiply it with the right hand side f. For that you may use matrix multiplication, matrix inverse, and you'll get the answer straight away. Now the answers for this turn out to be, and I want you to verify this, 7.49998 into 10 raised to minus 8. Now don't worry about this, this is 0. Then here you have 150000381, and u3 is equal to 0.1200000015. Now please notice, you need to apply as u1 is equal to 0. What actually you were able to apply was this, very close to 0 but not 0. Similarly, u3 you aim to apply 0.12, but actually what got applied was this. It's almost the same thing, but slight error. You can say this is error, but actually this is very close to the exact solution. Now what about the reaction forces? Reaction forces, again, how simple it is to apply the boundary conditions, and if you want to find the reaction forces, they are equally simple. R1 is, we went through this, is u1 minus a1. Now here the difference between what you sought to apply and what was actually applied comes into play here. So here minus c, you know what minus c is. This is 666.68 into 10 raised to power 6 into u1 value. u1 value is this, very close to 0 but still something, minus 0, and this turns out to be minus 49,000 999.88 newtons. R2 minus C, R3, there's no R2, there's R3. U3 minus A3, again minus 666,666.68 into 10 raised to the power 6 into U3. This is what you were able to apply actually, and this is what you sought to apply. This is U, this is A, U1, A1, U3, A3. This turns out to be minus 10,000.12 newtons. Now this, if you check this with the mechanics of material solution, you will, and you can guess it even right here, that actually it is minus 50,000 and this is minus 10,000, and you can confirm this with the mechanics of material solution. But this one has very slight error here, and that error is because you never end up applying the same value of the boundary conditions. Part of the error is this. The other part could be computational error, but this one has an extra component of error. And once you have these, you have verified your penalty method gives you the correct answers, and it is much simpler. This reaction forces calculation as well as the application of boundary conditions, much simpler than any of the partition methods you have studied before. Now this question was analysis question, so you were supposed to find out the stresses, but if you have found out the sigma, the u's, u1, u2, u3, from this to move on to epsilon 1 and epsilon 2 is no problem, and from there you can move on to sigma 1 and sigma 2 too. I'm not going through that process because that is not the part of today's lesson. You're so familiar with that you can do it. Here our purpose was to see how we apply the penalty method for application of boundary conditions, how simple it was as compared to the other methods, and how simple it is to calculate the reaction forces should we require the reaction forces. In most cases we don't require them, but if we do, there's nothing difficult about that either. Thank you very much.